Alright, this is the second lecture on benzene and aromaticity. I know I posted another lecture that covers a lot of the same topics from a different source, but there were a few things that I also wanted to touch on. So some of this might be redundant. If you watched that other video, you know that in order for something to be aromatic, it must be cyclic, planar, completely conjugated, and of course what that means is that all atoms, not just the carbons, but all atoms must be sp2 hybridized, and it must contain a particular number of pi electrons. Remember, for an sp2 hybrid, we've hybridized an s orbital, two p orbitals, and then we have an unhybridized orbital, so it has two lobes, right? So the unhybridized orbital is what makes the pi bond. So the criteria we're looking for must be cyclic, planar, completely conjugated, and a particular number of pi electrons. This is Hückel's rule. So Hückel's rule, the number of pi electrons must equal 2 plus 4 times some integer n. So actually not integer, it could be a whole number as well. So the Hückel's rule could be 2 and then 6, so n is 0 here within the case of 2. 6, n is 1. And then simply adding 4 more pi electrons. So 2, 6, 10, 14, 18, etc. That's the Hückel's rule number of pi electrons. But again, it must also be completely conjugated, cyclic, and planar. So this compound here, 1,3,5-hexatriene, not cyclohexatriene, there's no bond here. This has Hückel's rule, but is not cyclic. And it would not be, would it be planar? Yeah, I think it would be planar, but it would not be cyclic, so it's not aromatic. Again, here they're just talking about how it must be planar. Now, cyclooctatetraene, right? This has 8. Right, so if for each double bond we have 2 pi electrons, so 2, 4, 6, 8 pi electrons. And not only does it not obey Hückel's rule, but it is also not planar. It has this tub shape. Molecule must be completely conjugated. I mean, all atoms must be sp2 hybridized. All atoms sp2 hybridized. So here we see a couple sp3 hybridized. If they're sp3 hybridized, there are no unhybridized p orbitals to overlap. Likewise here, sp3 hybridized. So the only one, these benzene, of course, aromatic, cyclic, planar, 6 pi electrons satisfying Hückel's rule and completely conjugated. All right, the number of pi electrons must be 2 plus 4n. There's also something called anti-aromatic. Notice anti-aromatic also has a chemical formula. It's 4n, so they lose the plus 2 part. So the number of pi electrons are simply multiples of 4. So clearly you can't have something with 0, so that wouldn't make sense. So it's simply 4, 12, 16, and so forth. Compounds that are anti-aromatic are actually especially unstable. So if they're aromatic, they're especially stable. Doesn't mean they're not reactive. We'll find that out in the next chapter. But compounds that are anti-aromatic are especially unstable. So something like cyclobutadiene is especially unstable. In order to be anti-aromatic, it must be, in order to be anti-aromatic, it must be cyclic, planar, completely conjugated. So that's just like aromatic, but instead of having this 4n plus 2, it has 4n pi electrons. So it's just like being aromatic, except for this one criteria. It has an anti-Hückel's rule number of pi electrons. Aromatic, anti-aromatic, we already talked about. A compound that is not aromatic, this would have 2 or more of the 4 criteria missing. So remember, it was cyclic, planar, completely conjugated, And then for the fourth one, we had two different criteria, 2 plus 4n pi electrons, or simply 4n pi electrons if it was anti-aromatic. So this is the 4n pi electron case, aromatic, 2 plus 4n. And something that's not aromatic is missing 2 or more of these. So maybe it's not cyclic, or maybe it's not planar, maybe it's not completely conjugated. Right? It doesn't really matter how many pi electrons there are if it's got, maybe it has a pi number or a Hickel's rule number of pi electrons, but it's not completely conjugated. Or a Hickel's rule of pi electrons, but it's not planar. Or maybe an anti-Hickel's rule of electrons, but it's not cyclic. Something I kind of glossed over in the first part, I'm not going to spend a lot of time on this either, but I want you to realize that one of the things that you can tell, say by experiment, if something is aromatic or not, is the highly de-shielded protons in an aromatic compound. So we have these highly de-shielded, says protons in sp2 hybridized carbons, highly de-shielded protons of aromatic hydrocarbons in this region. Okay, so cyclooctatriene, this guy is de-shielded somewhat because it's a vinyl, right? It's on an sp2. It's a vinyl hydrogen on an sp2 carbon, and it's also conjugated. It's also cyclic, but it's not. This is the one that has that tub shape, so it's not planar. And this is the only one that's like that. It's kind of odd, but its tub shape is not planar. And the reason for that is, I think they discuss it in the book, but it adopts that tub shape to move these atoms a little bit further apart. When you get to larger, let me talk about this too. I talked about annulenes. Benzene is an aniline. Benzene is 6-annuline. Cyclooctatetraene is 8-annuline. Right. When you get to larger annulines like 12, 14, 16, and so forth, then they tend to be planar because there's enough room in the molecule to accommodate the planarity. So this has a much greater de-shielding. One thing I should also mention, 8-annuline has 8 pi electrons. Well, this is that anti-Hickel's rule number of pi electrons. I'll put a little question mark here. But it's not anti-aromatic, and that's because it's not planar. So again, this is a case where we're missing 2 criteria. It doesn't have Hickel's rule. It's actually an anti-Hickel's rule. But it's also not planar, so simply not aromatic. Again, these annulines, if you simply count the number of pi bonds, 1, 2, 3, 4, 5, 6, 7. There's 7 double bonds. Remember, each double bond is formed from a sigma and a pi. So there's 2 electrons. I'll put one on the top, one on the bottom. 2 electrons per bond, so 7 times 2 gets you 14. Right? Now 14 is the number of carbon atoms. There's the reason it's called 14-annuline is because there are 14 carbon atoms. Right? It's C14. Not when I say C14, I don't mean the isotope C14. I mean there's 14 carbons, and there would be 28 hydrogens. Is that right? No. It'd be also 14 hydrogens. C14H14. But the 14 also tells you how many pi electrons there are. 14 satisfies Hickel's rule, right? So it's, remember, it was 6, 10, 14, 18, 22, 26, and so forth. So it's cyclic. It's going to be planar because there's enough room here inside the ring for the atoms to adopt a planar geometry, and it satisfies Hickel's rule. So yeah, it's aromatic. Likewise with 18. So if you counted these up, there would be 9 pi bonds. There would be 9 pi pi bonds. So 9 would give you 18 pi electrons times 2, 18 pi electrons, and it would be C18, H18. This also satisfies Hickle's rule, is cyclic, planar, completely conjugated. Again, another example here, 10-aniline. All right, 10-aniline satisfies Hickle's rule, but it's not planar. So it has a kind of a little twist in the molecule. So what it was, 8-aniline was tub-shaped, aniline, tub-shaped. 10-aniline is has a little pucker or twist in it. So I'll just say it's puckered. So these are two examples where they're not planar. So if they're not planar, it doesn't matter if they have Hickle's rule or anti-Hickle's rule. We're missing 2 or more of those criteria, so it is not aromatic. So these are simply not aromatic or non-aromatic, same thing. Don't confuse these anilines with these polycyclic aromatics that I think we talked about before. Naphthalene, you should know the name of this compound. It is found in, well, it is the active ingredient in mothballs or moth flakes. And then there's also anthracene and phenanthrene. These are carcinogenic, found in cigarette smoke, and also the other one was benzpyrene. So don't smoke. You'll inhale these things and get lung cancer. Heterocyclic aromatics. So what do we mean by hetero? It means they have a heteroatom. So some atom other than carbon. And usually what we're talking about is either nitrogen in this case or oxygen. Same criteria you have to go through, but because nitrogen often has 2 unshared pairs and oxygen, has 1 unshared pair, oxygen has 2 unshared pairs, it gets a little bit more complicated. They talk about this system here, but what I really want you to focus on is the fact that, even in ammonia, right? Ammonia has an unshared pair. Water has 2 unshared pairs, right? So oxygen, 2 unshared pairs, nitrogen, 1 unshared pair. It's typically what you'll see. Well, until we start talking about ions. So is this compound aromatic? Well, it's cyclic. It's planar. Now, normally, this nitrogen, right? This nitrogen here in ammonia is sp3 hybridized. Here they're saying it's sp2 hybridized. Well, why is that? It's almost as if, and of course, nitrogen atoms don't have a brain. They're not thinking about this. It's just a matter of thermodynamics. Remember, one of the driving forces in nature is always to go to the more stable state. So it has a choice. It could be sp3 hybridized or sp2 hybridized. If it's sp3 hybridized, we'd have 2 plus 2. If this is sp3 hybridized, this unshared pair of electrons is going to be in a hybrid orbital, not in an unhybridized p orbital, which means these are not conjugated. So it would be not conjugated. We would have an anti-Hickle's rule of pi electrons then, because there would just be 2 plus 2 is 4, right? So I just say 4 pi electrons. So it either has this choice, or it could be sp2 hybridized. If it's sp2 hybridized, it will then be completely conjugated. And we have 2 pi electrons, plus 2 more is 2, plus 2 is 4, plus 2 more is 6. 6 pi electrons, right? 6 pi electrons tells us that it satisfies all the criteria for aromaticity. So therefore, this pyrrole, so it's a cyclopentane ring, if you wish, but one of the atoms is a nitrogen. These 2 electrons, if you wish, you could anthropomorphize it, they decide to be in an unhybridized p orbital. Here's a good hint here. When a heteroatom is already part of a double bond, right? Well, if it's double bonded, this heteroatom, we'll just call it X. Again, it's usually nitrogen or oxygen. It must be sp2 hybridized. Just kind of default by definition if it has a double bond. It's only when it has a single bond that you have to kind of think about things. So this this nitrogen definitely sp2 hybridized because it forms a double bond. The question then is, are these electrons, these unshared electrons, are they going to be in a hybridized orbital or an unhybridized orbital? So again, for nitrogen, let's just do the whole electron configuration. Nitrogen is element number 7. 1s2, 2s2, 2p3, right? So this is its electron configuration. If we hybridize this, now it's going to be sp2 hybrid. Sorry, sp3, I forgot the 3. Oops. I can erase that one guy. There we go. Okay, 1s2, 2s2, 2p1, 2, 3, 3 single electrons. This is what it would look like, say, in the ground state. So this is ground state. If it's sp3 hybridized, what does it look like? The first two, the inner core electrons, we don't mess with, but we're going to mix an s and 3 of the p orbitals. So it's going to look exactly the same as we did before, except that all 4 of these, the s and the 3 p orbitals, all have the same energy. Okay, so that's this is sp3 hybridized. sp2 hybridized, again, 1s we don't mess with. We're going to mix an s and 2 of the p orbitals. I'm going to make this, okay. If you recall, sigma bonds are formed from the hybridized p orbital. So this is, I just put here sigma bond. The unhybridized p orbital, again, this is sp2, so an s and 2 p's. This is an unhybridized p orbital. It has 2 lobes, right? This is what is used to form the pi bond. Well, if this guy is sp2 hybridized and we have a double bond, that means this electron has to be in the in the unhybridized p orbital. That means these 2 electrons that are paired up are in the sp2 hybrid. Let me draw just this atom. So we have 1, 2. That's these 2 guys in an unhybridized p orbital. We have 1 electron here forming a sigma bond. We have 1 electron here forming a sigma bond. But then we also have the unhybridized p orbital. That's this guy. Right. So these 2 electrons, right, they're going to be in an sp2 hybrid orbital, not in an unhybridized p orbital. Likewise, these 2 here doesn't mention it, but this would be, actually this would be in the sp3 hybrid orbital. That would be these 2 guys here. Here we get into a little bit different case. This nitrogen, I'll draw it over here. We have a bond to a hydrogen, so 1 electron. Now let's do it this way. Okay, so we're forming, we're forming a bond here to a carbon, and it's a single bond, so fine, that's one of these guys. A single bond to this carbon, fine, that's this electron. Single bond to the hydrogen. In fact, we can put the hydrogen electron in here as an X. So these are sigma bonds. They're all single bonds. What about the unshared pair here? Is it going to be in an unhybridized p orbital, or is it going to be in an sp3 hybrid? Well, if we have 2, 4 electrons here. Now, if this was not sp2 hybridized, if it was sp3 hybridized, let's look at these options here. For this nitrogen, if sp3 hybridized, these 2 electrons would be like these 2 guys here, okay, in a hybrid orbital. That means 2 things. First off, it would have only 4 pi electrons. So you think, oh, it's anti-aromatic, right? That's an anti-Huckel's rule of pi electrons. But it's not completely conjugated. So I just say here, not conjugated. So what does that mean? That means that if it was sp3, it would be non-aromatic. Well, what's our other option? We could be sp2 hybridized. So if it was sp2 hybridized, we can put, I'm going to put both electrons here to kind of emphasize the fact that we've got 2 electrons in this unhybridized p orbital. It's going to look kind of like this, but let me write this be 1s2 sp3 sp2. We've got 3 single electrons in the sp2s. That's forming the sigma bonds. So that's our sp2 hybrid. But of course, nitrogen is in group 5. It has 5 valence electrons. So 1, 2, 3. That makes these 2 guys in an unhybridized p orbital, and it forms a pi bond. So they're pi electrons. So the other option is that it's sp2 hybridized, and then okay, we've got it cyclic, we've got it planar. It'll be completely conjugated because all these atoms are sp2, and we'll have 2, 4, 6 pi electrons, so it satisfies Huckel's rule. So this guy is going to be aromatic, and it's not like the electrons have a brain and they can think about which way they want to be. They just adopt the condition that makes them more stable. So this nitrogen here is going to be sp2 hybridized. This ring here will be aromatic. And here we have a case of unshared pair of electrons being in a pi bond, or unhybridized p orbital. And in the same compound, in fact just 2 atoms away, we have an unshared pair of electrons being in a hybridized orbital, and it's they're not used to form a pi bond. In fact, they're not bonding at all, right? They're non-bonding electrons. These 2 electrons are these 2 electrons here, and then we have sigma bond, sigma bond. So these 2 guys form the sigma bonds. These are the unshared pair, right? And then the double bond is formed by this electron in the unhybridized p orbital. Little practice for you. Which are aromatic? Yeah, we'll do these. Okay. So it's cyclic, it's planar. Is it completely conjugated? Well, we have double bond, single bond, double bond, single bond. If this atom is sp2, now remember oxygen? Remember now oxygen is going to have 2 lone pairs. If it's sp2 hybridized, then it would be conjugated. It would be cyclic, of course, still cyclic. It's planar. How many pi electrons? 2, 4, 6, 8? No. If it's sp2 hybridized, right, we have electron here. Oxygen 1s2, 2s2, 2p4. It has 6 valence electrons. Right. If it's sp2 hybridized, we're going to hybridize an s and 2 of the p's. Okay. We have 2 single bonds, 2 sigma bonds. Right. Well, we've got a single electron here that can form a sigma bond. Right. It's in a hybrid, but we don't have any others. So what I'm going to do is I'm going to remove one of these guys, put it out here. See if I can erase this one. There we go. So fine. Sigma bond, right, in the unhybridized p orbitals. That means we have one pair of electrons. It doesn't really matter which one you choose, but actually let's just to make it fun and colorful. Okay. The blue guys, these will be pi electrons. They're in the unhybridized p orbital, right? P sub y, p sub x, p sub z. The other pair is in the hybrid. So these are, let me say, in an sp2 hybrid orbital. So if it's sp2 hybridized, fine. 2, 4, 6 pi electrons, cyclic planar, completely conjugated. But on one single atom, one lone pair is going to be in pi, forming pi electrons in the unhybridized p orbital, call that p sub z, and the other pair in the sp2 hybrid orbital, so not counting, of course, towards the pi electrons, just these two. Let's do the next one here. Let's put in the unchaired pairs. Nitrogen, unless there's a charge here, you know, nitrogen usually forms 3 bonds, and when it does, it's got one lone pair, right? 1, 2, 3 bonds, so a lone pair here. Because these are involved in a double bond, they must be sp2 hybridized. So we have double bond, single bond, double bond, single bond, double bond. It's completely conjugated. All the atoms are sp2 hybridized. How many p electrons do we have? 2, 4, 6. Right, in this double bond, we've got 2 pi electrons. That means neither of these two lone pairs are in an unhybridized p orbital. Both of these guys, both lone electron pairs, are in a hybridized sp2 orbital. Right, remember, in order to be counted as pi electrons, they must be in an unhybridized p orbital. Right, unhybridized p orbital that has 2 lobes. Okay, what about this guy? Well, it's cyclic, 6-membered ring, to be planar, 2, 4, 6 pi electrons. Now notice this oxygen has 3 bonds, and so it has a plus charge. You can have aromatic or anti-aromatic ions as well. So what we've done here is, normally oxygen has 2 lone pairs when it forms 2 bonds. When it forms 3 bonds, it's got a plus charge, and now only 1 lone pair. Okay, so this oxygen, of course, it's in a double bond, so it's going to be sp2 hybridized. The double bond, that means we've got 2 electrons here in an unhybridized p orbital. All right, so what does this orbital diagram look like? 1s2, 2s, 2p, and we've got 1, 2, 3, 4, 5, 6 valence electrons. If it's sp2 hybridized, we're going to combine an s and 2 of the p orbitals. Okay, so what we need to do here is remove one of these guys, stick him out here in the unhybridized p orbital. So we have these 2 electrons here in sp2 hybrid, right? This is our sp2 hybrid. We've got a sigma bond and a sigma bond. That's these two. And then the pi bond, the double bond here, is formed by these two electrons. So there's two electrons, both from the oxygen, forming that pi bond. This is cyclic. So it's cyclic. It's planar. It's completely conjugated, and it has 2, 4, 6 pi electrons. So this guy is aromatic. This next one here would be non-aromatic. Let me put the unshared electron pairs in here. Double bond, single bond, single bond. There's no way to really, we have two, it's cyclic, planar. We have 4 pi electrons, which would be the anti-Hickels rule, except it's not completely conjugated. Again, ions can be aromatic. You notice in these resonance structures, as I was saying before, the resonance structures must have the same charge. So negative charge, negative charge, negative charge. They all have one negative charge, and we're just moving the electrons around. This guy is aromatic. We have 6 pi electrons, 1, 2, 3, 4. This carbanion, doesn't matter where we move it, this carbanion has 2 pi electrons, so 6 total pi electrons, and this would be sp2 hybridized. Now sometimes carbanions, I should mention this, carbocations, they are always going to be sp2 hybridized. Carbanions, they're the ones that kind of have a choice. Carbanions, the carbanion, if it's this, so let's just make it hydrogens, but it wouldn't be hydrogens. But anyway, so sigma bond, sigma bond, sigma bond. This is the way I've drawn it, this is sp3 hybridized. That extra electron here is in an unhybridized p orbital, right? Or is in a hybridized p orbital. So here's an sp3 hybrid, here's an sp3 hybrid, here's an sp3 hybrid. So 4 hybrid orbitals, sp3, or it could be sp2. So again, these are those hybridized p orbitals. We got 1, 2, 3 electrons, and then an unhybridized p orbital here. Unhybridized p orbital. So carbanions can be sp3 or sp2 depending upon which conformation is more stable. Carbocations always sp2, and that's just what they're showing you here. In this case, it decides to be sp2 hybridized. What about the cyclopentadienyl cation? If it's a carbocation, like I said, it's always going to be sp2 hybridized. So fine, it's cyclic, planar, completely conjugated, because this carbon here with the carbocation is sp2 hybridized, but only has 2 4 pi electrons. This is anti-aromatic, so it's very unstable. The cyclopentadienyl anion, 4n plus 2 pi electrons, right? We just talked about this guy. This guy is aromatic, it's stable. What about this one? The cyclopentadienyl radical. Now we haven't really talked about radicals much. Radicals have an odd number of electrons. Okay, so what that means is not all the electrons are paired up. In a bond, right? If it's a sigma bond, fine, we have 2 electrons forming that bond. If we have a pi bond, like in a double bond, we have 2 electrons, or if we have a lone pair, fine, they're paired up. But a radical is a single electron, not paired up. So we talked about it as a singlet electron. Well, whether it's anti-aromatic, 4n plus 2, doesn't matter what n is, we're always going to end up with an even number. Likewise here, always an even number. If it's any sort of radical with a single electron, we have an odd number of electrons, it's got to be non-aromatic. They will have neither the anti-aromatic 4n plus 4n pi electrons or the aromatic 4n plus 2 pi electrons, because these are always even number of pi electrons, also even number of pi electrons. Radicals will be an odd number. Okay, lastly, aromaticity and acidity. So we talked about acidity way back when. Let's talk a little bit about ways, I just say factors that affect acidity. Okay, one of the things we talked about was elemental effects. You can go back to chapter 2 and look that up. As elemental effects, there's inductive effects if we have some electron withdrawing groups. We had resonance. And that's kind of what we're going to be talking about here. So this compound is not aromatic, pKa of 15. Okay. If we remove one hydrogen, right, now we have 2, 4, 6. This will be sp2 hybridized, and it's aromatic. Why is this a big deal? Well, let's look at, they don't have it here, but let's just put one double bond in here like that, and right. So a base comes along, abstracts that hydrogen, hydrogen here, unshared pair. All right, this is non-aromatic. Both of which are non-aromatic, the acid and its conjugate base. The pKa here, the pKa of most sp3 hybridized carbons, I don't know if you know what this is, but it's about, I don't know, it's 50 or 60. Here, it's 15. That's an insane, power of 35 or something. Insanely more acidic. So 10 to the 35 times more acidic than a regular sp3 hybridized hydrogen. So, and of course the reason for that is the conjugate base is now aromatic. And we could also, if you want, we could draw resonance structures. We can put this pair of electrons in here, move that pair of electrons out, have the double bond here, move that carbanion out here now. And there's of course another one as well, where we move the remember when you do these resonance structures, the negative charge often leapfrog, so you can skip one here and you can skip another one up there. All right. So now we also have not just resonance, but aromaticity. Put a question mark there. If the conjugate base that you form by removing or abstracting a proton makes the compound aromatic, it's going to be much more acidic. Here, they're just talking about the fact that this shows resonance, so I just draw a line here. Resonance. Here there's no resonance. That's because this is an sp3 hybridized carbon. And so with resonance you see a big difference, but nothing like what you can see between a regular sp3 hybridized carbon and the hydrogen in this cyclopentadienyl anion. Okay, last slide. Real quick. Diamond. All the atoms in diamond, so there's these three allotropes of carbon. Diamond, graphite, and C60 or Buckminster fullerene. Diamond, these are all sp3 hybridized. Let's try to pick here this guy here, right? Let's pick this carbon here. It's got 1, 2, 3, 4 bonds. It's tetrahedral. They're all sp3 hybridized. In graphite, if you notice here, this is a benzene ring, this is a benzene ring, this is a benzene ring. They're all sp2 hybridized. So yeah, graphite is aromatic. Diamond, non-aromatic. And one of the interesting things about graphite, you might be familiar with graphite as a dry lubricant. I'll just say used as a dry lubricant. And the reason for that is there are these pi bonds that interact with one another between these sheets, or what we call glide planes in crystallography. And there's this weak interaction, these weak intermolecular forces of these pi electrons, these pi clouds in one sheet compared to the next, and that allows these sheets to slide over one another, and that's what makes it act as lubricant. You actually have one sheet of graphite sliding over another sheet of graphite. What about Buckminster fullerene? Well, if you remember what I said earlier about radicals, each carbon also has a p orbital with one electron. Well, okay, if it's got one electron, this is a radical. That means it has an odd number. That means it can't be either aromatic or anti-aromatic. This is simply non-aromatic. All right. So that will do it for this chapter on benzene and aromaticity. In the next chapter, we will talk about reactions of benzene.